All right, so this is lesson one, igneous rocks. So basically, how do rocks form from magma? So magma is molten rock that's underground, and then lava is molten rock that's above ground. So basically, how they form from magma would be that they're underground and they're forming and cooling very slowly because they haven't erupted onto the surface. All right, so a review from the last section. A silicate is silicon and oxygen combined together. And these are some examples, some really common examples of silicates. So you guys looked at quartz the other day. I did not have you guys look at the other things, but we've got pyroxene, mica, feldspar, olivine. These are the most common. Olivine is really common around here. If you hike up anywhere in the Trinity Alps, you'll see a lot of olivine, and then around Shasta Dam, there's a lot of olivine as well. And feldspar is a really common rock around here as well as quartz. So silicates are just made of silicon and oxygen. All right, and then igneous rock is when you have magma or lava forming a rock. So the magma or lava crystallizes and forms something solid, which would be an igneous rock. Remember, magma is underground, lava is above ground. So they're both molten rock, it's just where it's found. So this would be an example of lava in the picture there. So we've got different compositions of magma, and that's kind of what makes up these rocks. So it depends on what minerals are present as to what the rock looks like. So it's classified as basaltic, andesitic, or rhyolitic. So basaltic, this would be a great example of basaltic. This is a special kind called so it's kind of chunky lava that is cooling and forming kind of a chunky rock, and it's very dark. So basaltic tends to be very dark colored, like Hawaii, and then andesitic is kind of a light, kind of a medium, I guess, color, and then rhyolitic is kind of a reddish tint. And kind of light colored. So we have here in Redding and Lassen area, we have a combination of andesitic and rhyolitic. We really don't have a lot of basalt. That's really common of volcanoes that come out of the ocean, like Hawaii, for example. All right, so our types of magma, you can see they're kind of categorized by silica content. And then later on when we talk about volcanoes, if the volcano is going to be really explosive or kind of runny, then it has to do with the silica. So the more silica, the more explosive the volcano is. So we can see with basaltic, it's the silica content is kind of half. So a good example here would be the Hawaiian Islands. And then andesitic, a little bit more, and the Cascades, which are Lassen, Shasta. And then rhyolitic, I said we did have a little bit of rhyolitic here, which we do. We're kind of a combination of rhyolitic and andesitic. But rhyolitic would be really typical of Yellowstone, which is super explosive. It's actually a super volcano. So it just has to do with the silica content. The more silica you get, the more explosive the volcano is. All right, so magma can be formed by melting rock, and that could be either the crust melting or it's melting inside the mantle. And the four main things that involve the melting of rock would be temperature, pressure. So the higher the pressure, the lower the melting temperature. Water content, same thing here. The more water you have, the lower the melting temperature. So that means ocean crust, then that contains a lot of water. And so as that melts, it melts actually at a lower temperature than just normal crust. And then the minerals. So for example, quartz melts at a really low temperature, whereas olivine melts at a really high temperature. So it just depends on what the rock's actually made out of. So here we can see this kind of gradient, and we can see, let me move my little picture. So we can see that temperature. So temperature is on the left here on the y-axis, and then on the x-axis is depth. And so as you get deeper and deeper, it tends to get hotter and hotter. So you can see up in the mantle, we have lower temperatures. And then as you get deeper and deeper into the crust, you can see the temperature increases and then kind of tapers off towards the core. So that's the geothermal gradient. So the deeper you go, the higher the temperature in Earth. All right, and then pressure, I said pressure also increases as depth increases. So pressure is just the amount, pressure is just the amount of squeezing force. So if you go deeper into the earth, you have more of earth pushing down. So that creates more pressure. And if you increase the pressure, that also increases the temperature, and the melting point increases as well. And so water also plays a factor in that. So if you've got pressure and water, it's going to change the melting temperature than if you just had the same kind of rock on the surface. All right, and they melt at higher, lower temperatures also because of what they're composed of. So like I mentioned, quartz is lower melting temperature than olivine. So basically rocks that contain iron and magnesium, they melt at higher temperatures than rocks that contain more silica. So the more silica they have, the lower the temperature tends to be. And we can also have in a rock partial melting. So that means that part of the rock melts, part of the rock doesn't. Just like I always give the example of like a chocolate chip cookie. So a chocolate chip cookie has the chocolate chips, it has the cookie part. Let's say that you leave it in your car. So if you leave it in your car, the chocolate chips are going to melt, like in the hot car. The chocolate chips will melt first, but the cookie gets soft, but it doesn't melt as much as the chocolate does all over the place. And so those have different melting temperatures. And so rocks are the same way. So a rock that contains a variety of different minerals, it's going to melt at different temperatures. So you've got really high temperature melting, really low temperature melting. So not all the rock is going to melt at the same time. And so that's what's called partial melting. So think of the chocolate chip cookie where part of the cookie melts, part of it doesn't. All right, so if we have partial melting, this is what we would see. So here's a solid rock, and you can see these are the different minerals that are contained in that rock. And then notice how it partially melted. So the hornblende did not melt, the biotite didn't melt, potassium feldspar didn't, and then what did melt is the quartz. So you can see quartz is not listed in here. And then the plagioclase is not listed as well, but everything else is still solid. So that would be partial melting. And this occurs often. So the whole rock doesn't always melt. All right, and so this reaction series explains how it melts and what temperatures things melt at. So I'll show you what that looks like here in a minute. But it just shows how rocks melt and also how they crystallize, which means hardens. So here's that Bowen's reaction series. And you can see down at the bottom, it lists muscovite, mica, potassium feldspar. So those are things that are a low temperature. So you can see on the right-hand side, low temperature, they crystallize faster. Sorry, they crystallize faster than the other things do. So these things at the very top, these take high temperatures. So olivine, that's going to be the last thing to melt. Pyroxene, amphibole, biotite mica. So this is kind of an order of melting. These things listed down at the bottom, the potassium feldspar, muscovite mica, quartz, those are going to melt first. So those are like the chocolate chips. And then the cookie part, the actual solid cookie part, that would be like the olivine. So that's going to melt last. And then when they crystallize, what crystallizes first is the olivine, because as it crystallizes, it's really hot, everything's melted. And then as it cools, it's going to go lower and lower in temperature. Well, as it goes lower in temperature, the olivine will crystallize first. And then what crystallizes last is the quartz. So just like a chocolate chip cookie, you take it out of the oven. The chocolate chips are going to, they're melty, right? So the cookie part is going to cool first and get harder. And then the chocolate chips will be the last to harden. And so that would be like our quartz. And then the first thing to melt would be the chocolate chip cookies. The last thing would be the cookie part. So that would be like the olivine. So that's kind of how rocks are too. So there's different parts that melt at different temperatures. All right. So iron-rich minerals, they are going to crystallize at different rates than the things that are silicates like feldspars. So feldspars would be our silicates. Iron-rich minerals, those would be our non-silicates. So that means they're not made with silicon and oxygen. And they do weird, crazy, fast changes as they cool. And so that's what makes, like when we look at the different rocks in the next few days, that's what makes the different, kind of like in granite, what makes the different big minerals and big colors in granite is the different types of minerals. So we've got iron-rich minerals, and then we also have the silicates, and they just crystallize and look different as it cools. All right, so when it starts to cool partially, so we had partial melting, remember, and then if it starts to cool at different rates, which it does, then as it starts to cool and harden, that's called fractional crystallization. So some of the minerals are going to crystallize first, and then others are going to crystallize last. And we get different shapes and different looks to the rock when that happens. All right, so we've got two types of rocks, and we can tell where they formed and how they formed by the crystals that are present. So if they formed outside on the surface of the earth, they're called extrusive. So I always think of extrusive as exterior of the earth. And then intrusive rocks form inside the earth, so they are intrusive. So intrusive inside, extrusive exterior is how I remember it. So they have different looks, and we can tell. I can pick up any rock and tell exactly how it crystallized. So if we look at these two rocks, the rock on the left does not, I don't see different minerals in there. I see kind of like veins and things, but I don't see different minerals like I do on the rock on the right. So the rock on the left would be an extrusive rock. The rock on the right would be intrusive. And so the reason I know that is because the rock on the right has a bunch of different colors in it. And so those are minerals. And those are referred to as granitic rocks. So granitic rocks form inside the earth. Basaltic rocks have lower silica content. They tend to be darker in color, like the rocks on the left. And that formed extrusively. And so, and it has to do with the minerals and things that are present. All right, so we have these different minerals here, and they show different colors. So remember, we have our three main types. We have basalt, we have andesite, we have rhyolite. This has more silica, the rhyolite, so it tends to be more explosive. Basalt tends to be more renny and not as explosive because it contains less silica. So rocks that are kind of in the middle, andesite, for example, they're called intermediate, and we have a lot of andesite around here. If you've ever really looked at the rocks, the majority of rocks, like around the volcanoes, tend to be andesite. All right, so here's our different types of rocks. We have our intrusive, our extrusive rocks. We refer to the texture as coarse-grained, porphyritic, meaning that it has large chunks and small chunks. Fine-grained means you can't see the other minerals. Like there's only one color and that's it. So think of like basalt. Like here, I'll go back. So this picture on the left, that would be an extrusive rock. It would also be fine grained texture. Whereas the picture on the right, that would be coarse grained texture. So, and then glassy would be like obsidian. You guys have all seen like an arrowhead. So that would be glassy. And then vesicular means that it has holes in it, like pumice. So pumice has little holes in it. And I'll show you these rocks in class. And then this just shows the different types of minerals that are present in these types of rocks. So we've got our granitic, our intermediate, our basalt. Our intermediate would be like the andesite, and then granitic would be like the rhyolite kind of rock. Basalt, dark, and then ultramafic. This is mostly reserved for in the mantle. So this would be mantle material, which would be ultramafic. All right, so texture, like I said, refers to the size, shape, or distribution of the crystals. So if I can see crystals in it, then it is intrusive, but it's also coarse. So here's some examples. So this one is glassy texture. That was obsidian that I was talking about. And that one is extrusive. And the reason I know that is because I don't see minerals in there. I don't see any colors except for black. And then this one on the bottom, this one is gabbro. And this one has large crystals and it's intrusive. So I can see different colors. So that means that it's intrusive. It formed inside the earth, cooled very slowly. So know the difference between extrusive and intrusive. So extrusive, no crystals. Intrusive, you can see crystals. Okay, that's the easiest way to remember it. All right, so this is what we refer to as porphyritic. So porphyritic texture is when you have it cooling slowly at first, and then for whatever reason, probably a volcanic eruption or something, it pushes closer to the surface and finishes faster. So it starts to cool slow, and then it gets pushed up towards the surface and cools faster. So notice how there's big chunks of rock in here, so big chunks of mineral, and then there's a smaller kind of grain in between. So porphyritic means, and I can tell if I were to look at this rock, if I were to walk outside and pick up a rock like this, I would know that it started to form underground, but then got pushed up towards the surface and finished cooling. So this is probably, if I were to date the rock and figure out how old the rock is, I could probably tell when there was magma movement or maybe even a volcanic eruption at that volcano. And then this is what we refer to as vesicular. So vesicular is, it's got little holes in it. So you can see this is a piece of scoria is what it looks like. But it's got little holes in it. And that's a vesicular texture. So pumice is a great example. Pumice actually has so many holes that it floats. It's the only rock that actually floats on water. All right. And then if we look under the microscope, and this would be like a special microscope, not the kind that you would see like in school. So this is a cross section, and it's a really thin section that we look at under a microscope. And these are different minerals. So we can see all these different minerals, and you can see the crystalline shape. So when you guys looked at minerals the other day, the data table showed crystal shape. And remember, I said we probably won't see that. That's because a lot of that is microscopic. So you can see the crystal shapes. These are like parallelograms, kind of like the calcite gypsum that you guys saw the other day. But you can see a variety of other things in here, and you can start to see the crystal shapes. These look like hexagonal shapes. This looks like a hexagonal shape. These are more like parallelograms. So you can start to see in different colors too. All right, and then veins. So sometimes we see veins in rocks, and that's when we, here in Northern California where the gold rush occurred, people sought after these veins because that's where we see silver and gold. And what happens is the water and the minerals become superheated and super saturated, and then it seeps through the rock and it leaves that deposit behind. And so it creates veins in the rock. So you can see that in this picture down here. So these are veins in the rock. So it looks like quartz in between basalt is what it looks like to me. But those are veins in the rock. And you can see the picture on the right as well. That's a really good example. There's a lot of that around here. You can see that. And you can pick up a tiny little rock and you can see that. Or you can pick up look at a big rock, a big cliff, and see that as well. And then sometimes we see pegmatites, which are just an ore. So you can see that here in the picture. So you can see this nice ore. And remember, an ore is something that we mine for a profit. So this could be like a gemstone. We might use that for jewelry or something along those lines. All right, and then kimberlites. Kimberlites is where we find our really valuable things like diamond. So in a kimberlite deposit, you see here it is. We've got this magma source, and then it's under very high pressure. This forms, and so we get carbon transformed in this case into diamond. And so we get, it's called a kimberlite. The rock type is a kimberlite. And so you can see right here, this is where they're mining. So this big, huge formation here is this big, huge formation here. And this isn't one big like diamond. Like we don't find just diamonds everywhere. But we do see diamonds found within it. So here in this rock, you can see these little crystals here. Those are diamonds. And they're uncut diamonds. And so they don't look as pretty as like a diamond that you would buy. They have to cut them, and then sometimes these rocks or these diamonds might not be really clear. They might be, not as valuable, but they're diamonds within that. And so they cut them like you would see in a typical diamond, but that's found in these kimberlite structures. Right, and that's it. I hope you enjoyed that, and I will see you next time.